And now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have a circle that is inside a semicircle. The small circle is inscribed by a semicircle. We know that side CD equals to 3 units, side DB equals to 4 units, angle CDB, this angle equals to 90 degrees, and we want to find out the radius of this small circle. Okay, so first of all, we'll make a construction. We'll complete the semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend line segment CD by a straight line until it touches the circle. And we will define the touching point of the extended line segment CD, and this circle is point E. And actually we extended the straight line CD by a straight line. And when you extend a straight line by a straight line, the result must be also a straight line. That is to say, CE is a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles here must be equal to 180 degrees. So which angles we have at this side of the straight line CE at point D? We have here 90 degrees. And we have also here angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. We will subtract 90 degrees from this equation, and we get that the missing angle EDB equals to 90 degrees. So angle EDB is a right angle, it is equal to 90 degrees. So we can write here that angle EDB, this angle is a right angle, it is equal to 90 degrees. Okay, so actually when we completed the semicircle to a circle, we created another semicircle. So actually the new semicircle is a mirror image of the original semicircle. I will repeat again. This new semicircle is a mirror image of this semicircle. Okay? And here we know that this angle CDB equals to 90 degrees, and angle EDB also equals to 90 degrees. Okay? And actually CD and DE, DE is the mirror image of CD. I repeat again, that line segment DE is a mirror image of line segment CD. Okay? And because of the fact that DE is a mirror image of CD, that is to say, the lengths of those two line segments must be equal to each other. That is to say, CD equals to DE, because the length of the mirror image must be equal to the length of the image itself. Because when you look at the mirror, you see yourself exactly with the same dimension that you have in reality, but in the opposite side. And because of the fact that DE is the mirror image of CD, it means that DE must be equal to CD by symmetry. Okay? By symmetry. And we know that CD equals to 3 units according to what is given us in the question. So CD equals to 3 units, and from this equation 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Okay, DE equals to 3 units. Okay, so we found out that DE equals to 3 units. In the next step, I will present to you a new rule. That is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, I'll repeat again, if two chords intersect with each other inside the circle, then the following equation is true. So we have actually here we have chord AB. This is chord AB that intersects with this chord CD. So chord AB intersects with the red chord CD at point O. We will define the intersection point as point O. I repeat again, chord AB intersects with chord CD at point O. then the following equation is true, that AO times OB equals to CO times OD. I will repeat again. Chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. And according to rule number 1, if this is the data that has been given to us, then according to rule number 1, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing, because in our drawing we have chord AB. This chord AB intersects with chord CE at point D. We'll write it down. Chord AB, this chord intersects with chord CE at point D. I repeat again. Chord AB intersects with chord CE at point D. I'll repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we will get that the following equation is true, that AD times DB equals to CE times DE. I repeat again, AD times DB equals to CE times DE according to rule number 1. Okay? AD is the missing line segment, so we will leave it as it is. Times DB. DB equals to 4 units according to what is given us in the question, so we will substitute DB by 4, and it is equal to CE. CE equals to 3 units according to what is given as the question, and we have already found out that DE equals to 3 units because DE is the mirror image of CD. So in conclusion, we found out that AD times 4 equals to 3 times 3. Okay? So here 3 times 3 is 9. So found out actually the 4 times AD equals to 9. Here we divide this equation by 4 and we get that AD equals to 9 over 4 units. AD equals to 9 over 4 units, so we can write down here that AD equals to 9 over 4 units, and AB, we know that AB is the diameter of the circle, of the big circle, and also the diameter of the semicircles. Okay, so I write it here that AB is the diameter of the circle and the semicircles. AB is the diameter of the circle and also the diameter of the semicircles. Okay? And we know that the diameter of any circle or semicircle is twice as long as the radius. So if we divide the diameter AB by 2, we will get the radius of the big circle and also the radius of the semicircles. We will define the radius of the big circle and the radius of the semicircles as capital R, and we will get that capital R equals to AB over 2. Okay? So from the drawing it is very easy to see that AB equals to AD plus DB. AB equals to AD plus DB, all divided by 2. AD equals to 9 over 4, and DB equals to 4, all divided by 2. So here we will multiply 4 by 4 and then we will divide it by 4 in order to the common factor with 9 over 4, and we will get that 9 plus 4 times 4 is 16 over 4 over 2. 16 plus 9 is 25. We have to divide it by 4 and also by 2. We'll move the 2 to the denominator and we'll get that it is equal to 25 over 2 times 4, that is 8. So in conclusion, we found out that R, the radius of the big circle and also the radius of the semicircles, it is equal to 25 over 8 units. Okay? In the next step, we will define the center of the big circle as P, and we will define the center of the small circle as Q. We will define the point of tendency of tangent CD with this circle as O, and from the center of the small circle, that is to say from point Q, we will draw the radius to the point of tendency, that is actually point O, Point O is the point of tendency of tangent CD with this small circle. So we draw the radius of this circle to the point of tendency. So CQO is the radius of the small circle because of the fact that point Q is the center of the small circle and point O is the point on the small circle itself. This is exactly the definition of a radius. So QO equals to the radius of the small circle. So we define the radius of the small circle as small r. And here we have the radius of this small circle that is equal to small r. It is drawn to point O, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius OQ. Again, CD is perpendicular to OQ. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from point Q, we will go perpendicular to the extended to the point of tendency. Again, from point Q, we will go radius to the point of tendency. We define the point of tendency of tangent DB with this small circle as point M. So from point Q, we will draw the radius of the small circle to point M. So here QM is the radius of the small circle, that is to say, it is equal to small r. And again, we have the radius QM of this small circle that is drawn to the point of tendency. That is to say, the radius QM is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, it means that the tangent DB will be perpendicular to the radius MQ. Again, the tangent DB will be perpendicular to the radius MQ. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? So actually, in quadrilateral OQDM, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle. Okay, so we relate to quadrilateral OQDM as a rectangle. Okay, so I'll repeat again. We will relate to quadrilateral OQDM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle OQDM, they are equal to each other. That is to say, OQ equals to DM. OQ equals to DM. I'll repeat again. In rectangle OQDM, the opposite sides are equal to each other. That is to say, OQ equals to DM. But we have already found out that OQ equals to small r, it is the radius of the small circle. So OQ equals to small r. So from this equation r equals to OQ equals to dm, we will derive that dm is also equals to r. Okay, we found out that dm is also equals to r, so we can write here that dm is equal to small r. Okay. And in the next step we will find out the length of line segment DP. Okay. From the drawing it is very easy to see that the length of line segment DP equals to DB minus PB. Again, DP equals to DB minus PB. So DP equals to DB, that is 4 units according to what is given as the question, minus PB. What is the definition of line segment PB? P is the center of the big circle. B is the point on the big circle itself. This is exactly the definition of a radius. That is to say, PB is the radius of the big circle that is equal to capital R. So in conclusion, we found out that dP equals to 4 minus capital R. dP equals to 4 minus capital R, but we have already found out that capital R equals to, here capital R equals to 25 over 8, so we'll substitute capital R by 25 over 8, and we get that dP equals to 4 minus capital R, that is 25 over 8. So here we will multiply 4 by 8 and then we'll divide it by 8 in order to have a common factor with minus 25 over 8. And we get that dP equals to 4 over 8, that is 32, minus 25 over 8. 32 minus 25 is 7, so in conclusion we found out that dP equals to 7/8. Here dP equals to 7/8. In the next step we'll find out the length of line segment PM. From the drawing it is very easy to see that the length of line segment PM equals to dm minus dP. Again, PM equals to dm minus dP. So PM equals to dm equals to r, according to what we have already found out, dm equals to r, minus dP, we have already found out that dP equals to 7/8. So in conclusion, we found out that PM equals to R minus 7/8. Okay? So we can write here that line segment PM equals to R minus 7/8. Now we can implement the Pythagoras theorem on the green right triangle, but before that, I will present to you a new rule that is actually rule number 2. According to rule number 2, if two circles have an internal notch between them, then the following equation is true. If two circles, it is actually, we are talking about rule number 2, this is actually a different rule. According to rule number 2, okay, we start with, if two circles have an internal notch between them, here in our drawing, the big circle have an internal notch with the small circle. At this point, we define the touching point between the two circles as point S. Point S can be defined also as the internal launch point. It is the internal launch point. Point S is the internal launch point, or the point of tendency, or the touching point, or the point of contact between the big circle and the small circle. So if two circles have an internal notch between them, then the straight line that connects their centers passes for the launch point. Okay, so I'll read rule number 2 again. According to rule number 2, if two circles have an internal notch between them, like in this drawing, the big circle and the small circle touch each other internally at point S. Point S is the internal notch point or the point of tendency. Then, according to rule number 2, the straight line that connects between their centers passes through the launch point. That is to say, if the center of the big circle is point P, the center of the small circle is at point Q, and the straight line that connects between the two centers is actually the straight line PQ, and here the straight line PQ passes through the internal notch points. That is to say, it passes through point S. So here we have, according to this rule actually, P, Q, and S, the 3 points P, Q, and S are located on the same straight line. Okay, according to rule number 2, the straight line that connects the two centers together is PQ, and this straight line PQ passes through point S, that is the internal notch point, or the point of tendency between the two circles. So you can derive from rule number 2 that points P, Q, and S points P, Q, and S are located on one straight line. Or in other words, you can say that line segment PQS is a straight line. Line segment PQS is a straight line. According to rule number 2, of course. Okay. So, what is the definition of line segment QS? What is the definition of line segment QS? Q is the center of the small circle. S is a point on the small circle itself. That is to say, this is the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. Okay? And what is the definition of line segment PS? P is the center of the big circle. S is the point on the big circle itself. That is to say, PS is the radius of the big circle that is equal to capital R. Okay, and we already found out that capital R equals to 25 over 8. So actually we found out that PS is the radius of the big circle that is equal to capital R, and QS is the radius of the small circle that is equal to small r. And what is the length of line segment PQ? The length of line segment PQ it is equal to, from the drawing it is very easy to see that the length of line segment PQ or QP it is equal to PS minus QS. PS minus QS. Again, QPS minus QS equals to PQ. I'll repeat again. From the drawing, it is very easy to see that the length of line segment QP equals to PS minus QS. Okay? So QP equals to PS. We already found out that PS equals to capital R minus QS. QS equals to small r. So in conclusion, we found out that line segment QP, this line segment QP equals to capital R minus small r. But we have already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. And in conclusion, we found out that QP equals to capital R, that is 25 over 8, minus small r. Okay, here QP equals to 25 over 8 minus small r. So we can write here that QP equals to, or PQ equals to 25 over 8 minus small r. Okay, so actually now we have all the sides of the right green triangle QPM. So we can implement the Pythagoras theorem on the right green triangle QPM, and we will find out the missing variable, that is small r. This is the line segment, the radius that we are looking for in this lecture, small r. Okay, so I'll copy the right triangle PQM in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle PQM. So actually, this is the right triangle QPM that I copied from the original drawing. We have already found out that PM equals to small r minus 7/8, and we already found out that the hypotenuse QP equals to 25/8 minus small r, and we already found out that QM equals to small r, that is the radius of the small circle. Now, so in the right triangle QPM, we will implement the Pythagoras theorem on this right triangle PQM. By PT is the abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ, the square of the hypotenuse is PQ squared, and it is equal to the sum of the squares of the perpendiculars, that is to say, it is equal to QM squared plus PM squared. Okay. So here PQ equals to 25/8 minus small r, so PQ square is 25/8 minus small r square, and it is equal to QM. QM equals to small r, so QM square will be equal to small r square minus PM plus PM square. PM equals to r minus 7/8, therefore PM square will be equal to r minus 7/8 squared. Here we will open the brackets on both sides of equation number 1, and we will get that according to equation number 1, (25/8 minus r squared) equals to 25/8 squared, that is 25 squared is 600, 25/8 squared is 64, plus r squared minus 2 times 25/8 times r. It is equal to r squared plus r minus 7/8 squared. It is r squared plus 7/8 squared is 7 squared, that is 49, over 8 squared, that is 64, minus 2 times r times 7/8. Okay, so here we have r squared on both sides of equation number 1, so r squared will get cancelled. And according to equation number 1, we found out that 625 over 64. Here we have minus 2 times 25r over 8. We divide both the numerator and the denominator of this expression by 2, and we get that minus 2 over 2 is minus 1, so minus 2 will get cancelled, and in the numerator we left only with minus 25r. In the denominator we have 8, so 8 over 2 is 4. So in conclusion, this expression equals to minus 25r over 4, that is equal to r squared plus 49 over 64, and here we have minus 2r times 7 over 8. Here we will divide both the numerator and the denominator of this expression by 2, and we get that minus 2 over 2 is minus 1, so minus 2 will get cancelled, and we left in the numerator only with minus 7r over 8, so we have to divide 8 by 2 also. 8 over 2 is 4, so in conclusion this expression equals to minus 4r, minus 7r over 4. Here we will multiply this equation number 1 by 64, and we'll get that according to equation number 1, here 64 over 64 is 1, so we left only with 625. Here we have here minus 25r over 4 times 64. It is actually minus 64 over 4, that is minus 16, times 25r. So in conclusion, this expression equals to minus 16 times 25r, that is equal to here r squared times 64 is 64r squared, and here we have 64 with 64 is 1, so we left only with 49, and here we have minus 7r over 4 times 64, so minus 64 over 4 is 16, so here, and this expression equals to actually minus 64 over 4 is minus 16, so this expression equals to minus 16 times 7r. In conclusion, so actually we found out that $625, according to question number 1, 625 minus 16 times 25r is minus 400r, and it is equal to 64r squared plus 49 minus 16 times 7r is minus 112r. Here we will add 400r to this equation number 1, and we get that according to equation number 1, we have here 625, 400r minus 400r is 0, so we left here only with 625. In the other side of the equation number 1, we have 64r squared plus 49, and we have here 400r minus 112r is plus 100, 200 plus 288r. Again, 400r minus 112r, it is equal to 288r. So here we will subtract 625 from this equation number 1, and we get that according to equation number 1, 625 minus 625 is 0. That is equal to 64r squared plus 288r. Here 49 minus 625, it is equal to minus 576. Okay, so here we have a quadratic equation. We will divide by 32 this quadratic equation, and we will get that according to equation number 1, 64 over 32 is 2, so this expression in total equals to 2r squared plus 288r over 32, it is equal to 9r. And here we have minus 576 over 32, it is equal to minus 18. And 0 over 32 equals to 0. So in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. Okay. Here, the coefficient a equals to 2. The coefficient b in this quadratic equation equals to 9, and the coefficient c equals to minus 18. And the variable that we are looking for in this quadratic equation is r, so x equals to r. And the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times AC over 2A. Here A, B, and C are the coefficients of the quadratic equation, and X is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is R, so X equals to R, so we'll substitute X by R. So R equals to minus B, B equals to 9, so minus B is minus 9, plus minus square root of b squared. B equals to 9, so b squared is 9 squared, that is 81. Minus 4 times a is 2, times c is minus 18. All divided by 2a. A is 2, so 2a is 2 times 2, that is 4. So here, the radius of the small circle r is equal to minus 9 plus minus square root of 81. Here we have minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So in the root we left only with 81 plus 144, all divided by 4. So here r equals to minus 9 plus minus 81 plus 144 is 215, so inside the root we left only with 215 over 4. So here we have r, the radius of the small circle, equals to minus 9 plus minus the square root of 200, actually here 81 plus 144 is 225, and the square root of 225 is 15. So here we will have two solutions that are possible for r. R equals to minus 9 plus minus 15 over 4. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6. That is a negative number. But because of the fact that the r is the radius of the small circle, or r is the length of the radius of the small circle, so r as a length, it must be, it is a length of the radius of the small circle, so as a length, it must be a positive number. Therefore, it can never be equal to minus 6, that is a negative number. So we'll cancel the solution, and we're left only with the second solution, that R equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6 over 4. Here we'll divide both the numerator and the denominator on this side of the equation by 3. 6 over 3 is 2. 6 over 2 is 3. 6 over 2 is 3. And 4 over 2 is 2. So in conclusion, we found out that R, the radius of the small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. Okay, I'll repeat again. R, that is the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. We finished the answer of this question. In the next step, I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we have here a semicircle. Inside this semicircle we have a circle, so the circle is inscribed by semicircle, and we know that side CD equals to 3 units, side BD equals to 4 units, and then again CDB, this circle equals to 90 degrees, and we want to find out the radius of this small circle. So in the first step we did the construction. We completed this semicircle to a circle, and then we extended line segment CD by a straight line until it touches the circle at this point, point E. Okay, so here we created here a second semicircle that is a mirror image of the original semicircle, and by extended, and here we extended the straight line CD by a straight line, so the result must be also a straight line. When you extend the straight line by straight line, the result must be also a straight line. So by extending the straight line CD by a straight line, we got CE, that is also must be a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles at this point, at this side of point D, must be equal, at point D, must be equal to 180 degrees. So which angles we have at point D? We have here 90 degrees, and then again EDB. Here, 90 degrees plus the size of angle EDB, in total they must be equal to 180 degrees. Okay, we subtracted 90 degrees from this equation, and we found out that this angle EDB, it is equal to 90 degrees. So this angle EDB equals to 90 degrees. Okay, as I already mentioned, the second semicircle that we created is a mirror image of the original semicircle. And then when we extended the straight line CD by straight line, we got line segment DE, that is also a mirror image of line segment CD. And because of the fact that line segment DE is a mirror image of CD, we will get that their lengths must be equal to each other. That is to say, CD equals to DE by symmetry. DE is the mirror image of CD, therefore CD must be equal to DE. And here we know that CD equals to 3 units, so we can write here that CD equals to 3 units according to what is given as the question. So from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Here DE equals to 3 units. Okay? DE equals to 3 units. Then here AB, first of all, I presented to you a new rule. This is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true. So here we have, in this circle, we have chord AB that intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 1, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing, because in our drawing we have the chord AB. This chord AB intersects with chord CE at point D. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, so I repeat again, here chord AB intersects with chord CE at point D. Therefore, according to rule number 1, we get that AD times DB equals to CD times DE. Again, AD times DE equals to CD times DE. Again, according to rule number 1, AD times DB equals to CE times DE. Here, AD is the missing line segment, so we leave it as it is. DB equals to 4 units according to what is given us in the question. So we will substitute dB by 4. C equals to 3 units according to what is given us in the question. And DE is also equals to 3 units according to what we have already found out. So here we have 3 times 3 is 9. So we found out that 4 times AD equals to 9. We divided this equation by 4 and we found out that AD equals to 9 over 4. Here the missing line segment AD equals to 9 over 4 units. Then we actually know that AB is the diameter of this big circle and also the diameter of the semicircles, and the diameter is twice as long as the radius. So if we divide the diameter AB into 2, we'll get the radius of this big circle and also the radius of the semicircles. We will define the radius of the big circle and the radius of the semicircles as capital R. So we get that AB is the diameter of the circle and the semicircles also, and capital R, that is the radius of the big circle and the radius of the semicircles, it will be equal to the diameter AB over 2. We know that the diameter AB equals to AD plus DB. Again, AB equals to AD plus DB divided by 2. AD equals to 9 over 4, DB equals to 4, all divided by 2. Here we multiplied 4 by 4 and we divided by 4 in order to have a common factor with 9 over 4. So here 4 times 4 is 16, is all divided by 4 over 2. 16 plus 9 is 25. And in the denominator we will move 2 to the denominator and we will have 2 times 4. 2 times 4 is 8, so we concluded and found out that the radius of the big circle, that is also the radius of the semicircles, it is equal to 25 over 8 units. The radius of this big circle and the radius of the semicircles equals to 25 over 8 units. Okay? Then we defined the center of the big circle and the center of the semicircles is point P, and we defined the center of the small circle as point Q. And from point Q, we defined the point of tendency of tangent CD with this small circle is point O, and we defined the point of tendency of tangent DB with this small circle is point M. Then from point Q we draw the radius to the point of tendency, that is to say to point O. That is the point of tendency of tangent CD with this small circle. So whenever you have a radius QO that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius QO. So if CD is perpendicular to QO, which means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay, and then we have from point Q, that is the center of the small circle, we draw the radius QM to the point of tendency, that is to say we draw the radius M to the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So if DB is perpendicular to MQ, this is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. So actually in quadrilateral OQDM we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3, that is 270 degrees. Yeah. So we have here 3 right angles, that the sum of them is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. In total they must be equal to 360 degrees. Okay, then we subtracted 270 degrees from the equation and found out that this angle 360 degrees minus 270 degrees, it is 90 degrees. So this angle equals to 90 degrees. Therefore quadrilateral OQDM that has 4 right angles must be at least a rectangle. So we related to quadrilateral OQDM as a rectangle. Okay, but we know that the opposite sides of a rectangle are equal to each other. So the opposite sides of a rectangle OQDM, they must be equal to each other. That is to say OQ equals to DM. OQ equals to DM. But we have already found out that OQ equals to small r. So we can write here that OQ equals to small r. And from this equation, we found r is equals to OQ equals to DM. We derive that DM is also equals to r. Here DM is also equals to small r, that is the radius of the small circle. Okay. Then we found out the length of the small line segment dp. From the domain it is very easy to see that dp equals to db minus pb. Okay, here dp equals to db minus db minus pb. db equals to 4 units according to what is given us the question. P is the center of the big circle, P is the point of this big circle itself. This is exactly the definition of a radius. So in conclusion, dP that is equals to dB minus PB equals to dB that is 4 minus PB that is the radius of the big circle that is equal to capital R. So in conclusion, dP equals to 4 minus capital R. But we have already found out that capital R equals to 25 over 8. So we substitute capital R by 25 over 8 and found out that dP equals to 4 minus capital R, that is 25 over 8. Here we multiply 4 by 8 and then we divide it by 8 in order to have a common factor of 25 over 8, and found out that dP equals to 4 times 8 is 32. 32 minus 25 is 7. So in conclusion, found out that dP equals to 7/8. here dp equals to 7/8. Okay, this small line segment, dp equals to 7/8. Okay, then we found out the length of line segment PM. From the drawing it is very easy to see that PM equals to dm minus dp. Again, PM equals to dm minus dp. PM equals to dm minus dp. dm equals to small r. We have already found out that dm equals to small r. dp equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. Small r minus 7/8. So we found out the value of PM, and then I presented to you a new rule that is actually rule number 2. According to rule number 2, if two circles have an internal length between them, then the straight line that connects their centers passes through the launch point. So here in our drawing we have the small circle is located inside the big circle, and those two circles touch each other internally at point S, this point S. That is to say, those two circles have an internal length between them, or the point of tendency of those two circles is at point S, and they have an internal length between them. So according to rule number 2, if two circles have an internal length between them, then the straight line that connects the centers together is PQ, and PQ must pass for the launch point that is S. So PQS is one straight line. According to rule number 2, here PQS are located on the same straight line, or PQS is a straight line, according to rule number 2. So we found out that PQS is one straight line, according to rule number 2. So what is the length of QS? Q is the center of the small circle. S is the point on the small circle itself, and this is exactly the definition of a radius. That is to say, QS is the radius of this small circle, that is to say it is equal to small r. Here. And what is the definition of PS? P is the center of the big circle, S is the point on the big circle itself. That is to say, this is exactly the definition of a radius. So PS equals to the radius of the big circle, that is equal to capital R. But we have already found out that capital R equals to 25/8. So PS equals to 25/8. Okay? And what is the value of QP? QP from the domain, it is very easy to see that QP equals to PS minus QS. Again, PS minus QS equals to QP. Okay? QP equals to PS minus QS. So QP equals to PS. PS is capital R minus QS, that is small r. So in conclusion, we found out that QP equals to capital R minus small r. Capital R is 25/8, so we substitute capital R by 25/8, and we found out that QP equals to 25/8 minus small r. Okay, so we can write here that the hypotenuse QP of the right triangle QPM is 25/8 minus small r. We have already found out that PM equals to small r minus 7/8, and QM equals to small r. So I copied the right triangle QPM in this new page, and we implemented the Pythagoras theorem on this right triangle QPM, and by implementing the Pythagoras theorem, we found out the missing variable here, that is small r, the radius of the small circle, the radius that we are looking for in this lecture. Okay, so here the hypotenuse PQ equals to 25/8 minus r. This side PM equals to r minus 7/8. and QM equals to R. And according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ, so the square of the hypotenuse is PQ squared. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QM squared plus PM squared. Okay? So PQ equals to 25 over 8 minus R, so PQ squared is 25 over 8 minus R squared. That is equals to QM squared. QM equals to R, so QM squared is R squared plus PM. PM equals to R minus 7/8, so PM squared will be equal to R minus 7/8 squared. We open the brackets on both sides of this equation number 1, and we found out that 25 over 8 minus R squared equals to 25 over 8 squared. 25 over 8 squared equals to 25 squared, that is 625 over 8 squared, that is 64, plus R squared minus 2 times 25 over 8 times R. We open, and if it is R squared, and we have also to add R minus 7/8 squared. R minus 7/8 squared equals to R squared minus plus 7/8 squared, that is 7 squared is 49 over 8 squared, that is 64, minus 2 times R times 7/8. So here we have R squared on both sides of the equation, so R squared will get cancelled. And in this side of the equation we have 625 over 64. Here we have minus 2 times 25R over 8. We divided both the numerator and the denominator by 2. Here minus 2 over 2 is minus 1, so 2 will get cancelled. In the numerator we left only with minus 25R. And here 8 over 2 is 4. So in conclusion, this expression equals to minus 25R over 4. And it is equal to R squared plus 49 over 64, and here we have minus 2R times 7 over 8. We divided both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so minus 2 will get cancelled. So in the numerator we have only left with minus 7R, and in the denominator we have 8. We have to divide 8 by 2. 8 over 2 is 4. So in conclusion, this expression equals to minus 7R over 4. Here we multiplied this equation number 1 by 64, and found out that 625 times 64 over 64 is 625. Here we have minus 25R over 4 times 64. It is actually minus 64 over 4, that is minus 16. So in conclusion, this expression equals to minus 16 times 25R. And here we have R squared times 64 is 64R squared. 49 over 64 times 64 is 49. And here we have minus 64 over 4 is minus 16. So in conclusion, this expression equals to minus 16 times 7R. Okay? So this is the expression that we got. And here we have here 625, and 16 times minus 16 times 25R is minus 400R. That is equal to 64R squared plus 49, and minus 16R times 7R is minus 112R. Okay? So here we added 400R to this equation number 1. So here we will have 625, 400R minus 400R is 0, so we left here only with 625. Here we have 64R squared plus 49, and 400R minus 112R, it is equal to plus 288R. Okay, so here we subtracted 625 from this equation number 1. 625 minus 625 is 0. Here we have 64r squared plus 288r, and here 49 minus 625, it is equal to minus 576. Here we divided this equation by 32. 64 over 32 is 2, so this expression equals in total to 2r squared. 288r over 32 equals to 9r. Minus 576 over 32 equals to minus 18. So in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18, and the variable that we are looking for in this quadratic equation is r. So x equals to r, and the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Here, the variable that we are looking for is r, so x equals to r, so we substituted x by r, and found out that r equals to minus b equals to 9, so b is minus 9, plus minus square root of b squared minus 4 times ac. B is 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c, that is minus 18, over 2a. A is 2, so 2 times 2 is 4. So here we got that r equals to minus 9 plus minus. Minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we left only with 81 plus 144. So here r equals to minus 9 plus minus root of 81 plus 144 over 4. Okay? 81 plus 144 is 225. So inside the root we left only with 225, and we found out that r equals to minus 9 plus minus 225 over 4. So the square root of 225 is 15, so in conclusion we found out that r equals to minus 9 plus minus 15 over 4. So here we will have two solutions that are possible for r, that is the radius of the small circle. R equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r, the radius of the small circle, equals to minus 6, that is a negative number. But because of the fact that r is the radius of the length of the radius of the small circle, as a length, it must be a positive number. R is the length of the radius of the small circle, therefore it must be a positive number. Therefore r can never be equal to minus 6, that is a negative number. So we cancel this solution, and we left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6. So we got that r equals to 6 over 4. We divided both the denominator of this side of the equation by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r, the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. I will repeat again, r, the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.